So, hello everyone, and by mistakenly I have started a recording instead of streaming. I'll be uploading the recording after this particular session.
So,
So,
hello everyone, and by mistakenly, I have
yes, so what I'll be doing, like you can just now I'm going to code the solution, but when I have solved this problem, that is recorded. So that is still recording. It was 53 minutes. So after this live stream, when it ends, I'll upload the 53 minutes video and you can just see that. And if really sorry for that because accidentally I clicked over start recording. I had to click on streaming. Now I'm streaming, so I will be jumping straight to the code, but yeah, I'll encourage you to basically first attempt the problem. And basically if you are here, so if you are, you can also see the solution if you already attempted. Now I'll be straight jumping to the code, right? So basically consider this as the part two of the basically the
encourage you to
so
basically
right. Okay, so by now I'll upload the entire recording. So this part which I'm streaming right now is basically the solution. So I have already come up with the logic how I will be executing it. If you want to see how I have came to this conclusion, you can just refer to my videos. In my videos, you can see the full video over there. Okay, so here we will be first implementing DFS to calculate edge nodes, and then we will be using BFS to traverse in levels. And then we will be executing this particular logic to get the uh, cached answer, right? And then we will just taking queries to answer everything. Okay, so we are just moving to the code section. Okay, so here this is the problem, and now let's check what is there in the requirements, right? Okay, fine. So now we will be jumping straight to the solution and right. So first what we have to do here is basically here we have to kind of first start with making this edge nodes, right? Edge nodes map. So I have this map which will be edge nodes. Edge nodes is a map which stores the data structure, data which stores the height below a particular node. For example, if edge node for this one will be the height below it, so it is 1 2 3, it will be 3. So this will be the data structure, and we need what do we need? And next we need map for the thing which is required. Basically, uh, it will be it will be answer I, right? But we have to return it in a different way. So I'll call this answer nodes, right? Answer nodes. And the answer which we have to return is basically this vector of int. It will be simply answer, which we will return later. So these are the data structure which we need for this. Now we will be implementing DFS and BFS, which will require their own data structures. For basically DFS, the data structure which is kind of used is just the stack, recursion stack, which is maintained internally, right? So here I'll just run this part. Basically, I will create a DFS. I'll create a DFS logic over here, and there will be some inputs. And here I need to do some things. Here I'll just execute this DFS with uh, with a starting point, with a starting node, which is the root node, and then you have to just give this particular edge nodes map to this. So I'll just pass the edge nodes map. Here I'll define the parameters. It will be First, it will be a tree node, which will be let's call it node, and then there will be this map of int, and we pass this via memory so that copies are not created and h nodes is actually updated. Fair enough. What is the base case? If we have the node that is not existing, in that case we return 0. If we have, now let's come to the node, right? So the depth below this is initially 0, right? Now if this particular node has a left subtree, so the depth will change to 1. So that element, if left exists, so depth is 1 for sure because it has one children, right? And then we will do the same thing, dfs over the child subtree, which will be basically tree node. uh, this will be basically node left, and then we have to pass the h nodes, right? And then same goes for the right subtree. So here in this case depth is equal to 1 plus dfs, and it will be node right subtree, and you just pass h nodes which will maintain the heights. Now since we are done with this particular node, we save this to h nodes. So h nodes of particular node value will be saved to the depth which we have calculated, and finally we have to return that depth. That will construct this h nodes thing. Now there are some limitations, I guess. The nodes, so there are two nodes for sure, right? So this root cannot be null. Fine. Now we have calculated h nodes. Now we have to execute this particular logic, which was to, again guys, again sorry, very sorry, I forgot to click start streaming. But yeah, this is a part of recorded session. So if you want to see that, I'll be uploading a video just after this stream, which will have from start till end, whatever is the solution. Okay, so this is the second part. Here I will be Here I'll be basically having some BFS logic, and inside this BFS logic, for each level, we will store we will store the nodes in some data structure, and then we have H nodes already ready in action, and then we can just execute this logic which we have here. Okay, so let us quickly set up the environment for BFS. So what we need for BFS, guys, we need a data structure which is Q, and which will be storing our nodes here, and let's call this Q. Okay, so we start by pushing the root node to the Q, and now while Q is not empty, we need to execute this. And as I told you earlier, we are also maintaining I, basically the level number beforehand. So after each level, we just increment I. Now what I need to do here, I'll need to extract the current queue. So current queue, I'll first calculate the length of the current queue. So integer L equals to Q dot size. Now while L, so now we have to extract all the elements which are there in the level, and I'll store them in a vector which is level nodes. And now what I need to do next is basically for each level I'll access the top element, I'll call it T, and it will be queue dot front, the front of the queue. And like which what we do in queues, basically when you access them, you just pop them. Now for the stop node, what you have to do, you have to push their children into the queue for the next further iteration. So if it has yeah, if it has left children, you just push that. If it has right children, push it like that. Makes sense? So BFS is there. Now what we you had to do over here was to push this particular node to the level nodes dot push back. It's a vector, and what you have to push is the value of this top node. Okay, so my bad, here it's actually D. It will be Q. Here it's T. Because T is the node which is under consideration. Right, so fix this syntax error. Now we have this particular BFS ready, and now we have the level nodes. We have created this particular level nodes here, and we have the edge nodes as well. Now it is the time to push them into the set, and you have to prepare this particular map to keep track of the values which they have. Okay, so there we go. So this will be a frequency map. And yeah, you have the answer notes here. Yeah, I think we are at the end of the solution, but it will be taking some sort of time. So here, for that part, there will be some data structures needed. First is a map, which will store the frequency of the nodes, heights, which will be frequency map, right? Which will be the frequency map. Makes sense. And then there will be a set, which will keep track of the maximum values. And maybe I can call this set. I can call this set. And basically, we need to access the element which is at the end of this set. And now it is not possible that the set is empty because there will be some level elements. If it is empty, that means like L is 0, which means Q is empty. It will not execute at the first place. Right, so here what we need to do is to basically iterate in the we need to iterate in the level nodes first, and we have to push these values. Yes, this is kind of very much a long step, I would say, but yeah, it is efficient, time efficient. So what we are going to do over here is basically this is uh, yeah. So here we are going to do this. Basically, we are moving this to frequency of x plus plus. So obviously we need to calculate the height h node of this particular level. So I'll call this LH node. So h node of a particular level, which will be h node x. And now you have to push this to the frequency map, which will be LH node plus plus. And then you have to push insert into the set, which will be LH node, right? And there you go, you have prepared these data structures. Now it's time to compute your answer for each particular level node, right? So I'll just go to this level nodes again, and what I will do here is basically yeah, so again I'll calculate the LH node, Now we have to remove this particular node from there, and we have to check what is the okay, so this is the case here. So basically what we have to find, uh, we have to find the max. So max element from the set, so that will be, I'll call it mx, and that will be accessing the reverse end of the set, right? This will return you the max element from the set, and we also need the second element, right? So let me do this. I'll just create an iterator which is at the reverse end, and here at this step we will just reference, we'll just access its value. And what I'll do to calculate the second max, so for that, uh, here I'll check if size of set is equal to 1. In that case, is not equal to 1, to be honest. So here we will have integer mx2, second max element, which will be 0. Yeah, well, let's keep it 0 for the time being. Let's keep it -1 because it is not existing. If it's not existing, then it's -1. So if it's not equal to 1, it means it's 2 or something greater than 1, right? So in that case, we just need to do we just need to go one step back, and we access the next max element. Why do we need two max elements? Because obviously, if we're going to remove a particular node from this particular level nodes, the max element can be the first max, or it can be the second max. It can be second max when we are removing the highest element itself. That's pretty much evident, right? Then we have this um, the second max, and if the second max does not exist, it means that there are no other elements than that. So in that case, we have to just basically deal with it. Okay, we have to just do -1 like we had discussed in the logic. So here what we will be doing is basically here we will be just removing it. So how we are going to remove it? Okay, so first thing first, if frequency of this particular LH node, if LH node is equal to mx, if it's the max element, and the frequency of that max element is 1, in that case, the max element from that entire level was this node itself, and there is only one max element. In that case, we need to have the second element mx2, right? And the answer node for this particular index in this particular x will be I, which we have from here, and then we have the plus mx2. So in that case, if mx2 exists, it will be like mx2 only. If there is no other element other than that, in that case it's -1, which is obviously true because there are no other nodes. It means that level is not considered, right? And else, there will be an else logic. You just add this answer node x is equal to okay, so we actually don't need to do -1 in the new logic which we had here. Were we doing -1, I equals to 2? No, we were just doing, yeah, there were some elements, right? So I was 3 over there, and 3 was the, yeah, so I is actual height. Yeah, we will need to do -1, it's fine. So it's fine, here it will be simply I plus mx. And there you go. I think we are done with the computation, and basically guys, this was the second part of the problem, which is quite simple only, not difficult. And this was the first part of the problem, understanding how you apply DFS and BFS together. Now we are ready with the answer. Now we are ready to take the queries which we have in our hands. Just minimize this part. Yes. So now we will be just moving to the queries for auto queue side queries. We have to do this answer.pushback answer nodes, and this will be queue, and then you just return the answer. Oh, it should be above this, right? Alright, so that has to be done. Actually, I have to change some variable names. This will be answer nodes. This will be answer nodes. I think we are done with the solution, and let me just run it. Um, okay, we are having some error in the. Oh, okay, so we have to pop the queue. Okay, so I have not used any kind of declaration here. It should be integer, right? Oh, so H node is not there. Is it H nodes? Okay, so it was H nodes. I hope I'm not using it more than one place. Wait. I think that is it. Yeah, these are the basically syntax errors which you can just solve it doing this. Case 1 was passed and we got the result. For case 2 there is some error, and what are we getting is this. But when we ran the pseudocode it was working, right? So we are having some sort of error somewhere. Let me just open this case. Wait, I'll just. Yeah, so this time we needed to debug this. Yeah, it's a kind of good experience as well, because unless you debug a particular test case, you're not going to get the full gist of it, full gist of your solution, okay? All right. So where did we mess up? Okay, this is some debugging part right now. Okay, so first I need to check if these things are calculated very much well. These DFS nodes, right? So I'll just go with I'll just go inside the edge nodes map and I'll just print. This will be x dot first, and there will be x dot second, and let me run this. Okay, so for node number 1 we have this 0, correct? 2 it's 1, 3 it's 0, 7, 4 it's 0, 5 it's 2, 1, 5 it should be 1, 2, 3. It should be actually 3. Okay, so I got it. So the basic mistake which I did was this. So this was the depth if you follow the left side, this was the depth if you follow the right side, and you have to take the max of these two depths, right? Seriously, my bad, guys. So I'll just use two depth variables. This will be depth L and this will be depth R. Depth of the left subtree and depth of the right subtree. And this is your depth of the, so this will be basically max of depth L, comma depth R, and same thing will be returned here as well. Let's run it up. What you get? Yes, so here it's 1. For 2 it's 1, 3, 0, 4, 0, 5 it's 3 now, 1, 2, 3, correct? 6 it's 0, for 6 it's 0, correct. 7 it's 0, correct. 8 it's 2, correct. Perfect. This one was true. Now I think this is working. This DFS is working, there is no issue in the DFS code. Now if we come to BFS, now how are we getting these 4 here? Let me just examine that. So first, basically what we were given query was 3. For 3, they have saved the answer as 4. How does 4 comes into picture? So here we will have level equals to I equals to 0, I equals to 1, and for this particular level it will be I equals to, so it will be 0 for this, it will be 1 for this, it will be 2 for this, right? It will be 2, and 2137, 2137, the max is 2, 1 and 3, 2 and 3 and 7, the max value is 1 only, rest other is 0. So in that case it would be, it will be 1 only, so it should be actually 3. Let me check guys, let me check for that particular level. Okay. Hmm. Yeah, I can just print it for the same node. We have prepared this set which has 0 and 1 in this case, and the value at the node 3 is 0, so the max which we have got in that case would be 0, would be 1, and mx2 should be -1. So for 3, if it's not like this, not like this, here we can do that, here we can do that, here we can do that. If x is equal to 3, just print what you are getting, the uh, mx and mx2. Yes, that's there. I'll just run it and let's check how is this working. It was 2 and 0, which is, you cannot get 2 at this level, any cost. At any cost you cannot get 2. How did you get 2? How did you get 2 at this level? Because there was 2137, right? Hmm. There were 2137, and for 2 the answer was 1, and yes, it was 1 only. So what did you do here was I was, let's print I as well. I plus mx2, I plus mx. It should be like 202. So I is correct. It is 0, it is right. I cannot get this, man. I cannot get this. Which node is basically 2? Uh, Wait, yeah. This is really okay. I can do this basically here. Don't this is correct in itself. It's correct. Here I just need to print a few things. What I need to print here is basically, yeah, if I is equal to 2, here I need to print um, x and its corresponding h node, h nodes x, or you can call it um, LH node, and this will be the end. And let's see how it works here. Yeah, so the values which you got over here were 1 only. So how did we got 2 as mx2, mx here? So we are pushing LH node over here only, right? edge node is, it's weird, man. Oh, okay, let me just do this thing here. I don't know, I have to make it. So here I'll just go with this particular step and I'll just iterate inside the set. After that, I'll just print mx and mx2. I should keep this in the if statement only. Let's run it. So here you are. Inside the set it's 0 and 1. There's the inside the set it was 0 and 1. But when you access the iterator, mx was actually mx was actually 2. How it is possible? mx2 is minus 1. There are two elements 0 and 1. So reverse end will be the iterator which is at the end, which is basically 1, right? It should be 1. Yeah, at this point it is there. Yeah, at this point only mx is calculated. mx2 is calculated here. But mx is not 2, man. Mx is 1. Because you have 0, 1 in the set. How come it could be that reverse end part? This does not make sense, man. I'll just do this st dot. Oh, it is r begin. My bad, man. It should be r begin. I'm accessing something which is beyond the limits, man. Which is some garbage value, I guess, mostly. Now it should pass the test case with ease. And this was the error. Also, there was some. Wait, there's some more errors. It should be 3232, but we are getting this. So now it is fixed, by the way. 0 and 1. So it is fixed for sure. And for the next case, we are getting 4. And for the level number 2, if we remove 2, we are getting 4. How are we getting 4 here? Because we are at 2, the value of 2 is 1. In that case, we will get 0 only. Yeah, I forgot to keep that in mind. SMX2. Basically, this should be done IT++, I guess. Not really sure, but let me check. Because this was some other garbage value. Yeah. Let me just remove these redundant comments. And where I have printed some statements, I have printed inside this as well. Okay, so I don't think now I have some garbage comments or something. I'll still check where I'm using cout in my code. Not using cout. Perfect. Let me just run this code. And guys, let's see how it is working. We got here some errors from where it is beginning. Okay, so it's like let me just check where did I mess up. Here it is messed up. We are getting this output and we are getting this output. I hope we are not missing any test edge cases. So let me just check the edge cases and verify it. Okay, let's come here. So the node values could be n is equals to 2. So there is no empty root node, and this approach seems good to me. Yes, it is. And then you have this queries, these are the queries, and this is the basically queries I is not equal to root value. Okay, so this is basically queries cannot be the root node, and there will be at least one query. That makes sense. Now let us try to submit this solution. I hope it passes. Yeah. So guys, this has actually passed it. And to be honest, this was a hard problem. And why it was a hard problem? It wasn't a hard problem because of the logic which you had to do. Basically, the way you had to solve this problem was very much straightforward. It was a hard problem because you were given uh, limited resources, you were restricted by some constraints, which made it hard. While the problem we solved last day, it was kind of a difficult problem to crack at the first level. So this was very easier to crack, right? And then when you started deciding the approach, the solution, then you had to really struggle, right? Then you had to really struggle how you can implement it. So implementation wise, it was a tough problem. How we are solving this, I'm just telling you in a quick overview manner. Okay, so let us come to this solution. So this is a very much quick overview of the code and how I have executed it. So so this is how we start. So there are two parts. First, you have to calculate what is the height of the tree from a particular node. So first you have to calculate what is the height below this. So it is 1 2 3. So it is 3 for node 5. The height below it is 3. For node 8 the height below it is 2. For node 9 the height below it, for in this particular tree, the height below it is 1. In here it's 2. For 2 it's 1. For 1 it's 0. For 3 it's 0. 7 it's 0. So first you need to calculate that, and for that I have used DFS. I calculated the respective heights at each node, right? And then I used BFS at each level. So for each level I have used BFS. What BFS is doing in this part is basically for each level we are checking what is the height below it and how much height we have covered from the top, right? So let's say if we are at this level, so we have already covered level 0, right? So we are at height 0. So now we check if removing this node, among the remaining nodes at this level, what is the maximum height we can go down. So for 9 it was 1. So it was 1 coming out to be 1. And now we were already at level 0. So we can go from level 1 to one more level down. So it will be 0 plus level 1 and then plus 1, which is 2. So for if we remove the node 8, the height of the tree would reduce down to 2. Now let's come talk about this particular 2 node. So for 2, the height below it is 1, and now we have already come down to one level. So from 5 to 8 we are sure that we have already come to one level. Now when we are considering 2, so now we have to remove this particular subtree. So we have to see what maximum height we can get out of these nodes, right? So I'll fetch their h nodes. After fetching their h nodes, I, I will I will just add it to this particular thing. So from here we had one height. Now we have removed this. We take the maximum out of this depth out of this. So here it's these are all zeros, so it's 0. So it is 1 plus 0 plus this level itself, which is 1. So it was coming out to be 2 for node 2, right? So for node 2 the answer was 2. So that's what we have done here. So we extracted all the level nodes at this place, and then we just executed the BFS logic where we took out all the level nodes, and then here is the another query, another logic basically, where we have calculated the answer for each node. If they are removed from the tree, what will be the height of the tree? For each node we calculated it, and then after calculation for each node Now we touched the queries, and since we already have had saved those answers, we just fetched it from the answer and just directly appended it to the answer, right? And then we return that answer array to the to this to the output, like to for the output of this particular function. Yeah, so guys, this was the entire gist about the problem. If you really want to see how I reached to this solution, you should check my full solution video, and I will be uploading it in 5 minutes. So yeah, that was it from my side, guys. If you have any question or any queries, you can just write in comment section. I'm available there to talk, and I'll address your queries in a very nice manner, right? So I hope we are done with the stream. I'll just check if it is still running. From my side, guys, if you have any question or any queries, you can just write in comment section. I'm available there. Okay, so it is I think it's done. So bye guys, take care and keep solving the questions. I'll be uploading the entire recording just after this call, after this particular live stream. And yeah, so that is it for today.